Planar graphs. So what is a planar graph? A graph which you can draw in plane without its edges are crossing. So such a representation of a graph is existing. In that case, you will call the graph is planar or embeddable in the plane. And any such representation of the graph, you will call it a plane graph representation. Okay. So you consider the graph G1, is it planar? The current representation of the graph or current diagram you are shown, it is crossing the edges, right? Other than that, at the vertices, if the edges are crossing, that is not a plane graph representation of the graph. So if whether the plane graph representation exists for a graph, this is what we are checking. If such a representation is existing, then you will call it a planar graph. So the same graph G1 I can draw in another form, right? So all these vertices and edges other than this crossing edge we have drawn. Now the crossing edge we have drawn through the outside, right? So edge need not be as a line segment itself will be coming, it can be a curve also. It's only showing those vertices are adjacent. So that vertices adjacency you can show it through outside. In that case, none of the edges are crossing each other. Other than at the vertices, these edges are not meeting. So this is another representation of the same graph G1, right? The same vertices, same pair of vertices are adjacent in both of them. Okay. So this is an isomorphic graph to G1. It's another representation of the same graph, and in this representation, none of the edges are crossing each other. Therefore, this is a plane graph representation. Since plane graph representation exists for your G1, G1 is planar. So G1 is a planar graph. Now, if you take K5, the complete graph on 5 vertices, or K33, which is complete bipartite with 3 vertices each in the partite sets, right? So those two graphs, they are non-planar. They are two examples of non-planar graphs. So this one, it was not a complete graph. It was containing 6 vertices. So it is not a complete graph. But if you take the complete graph on 4 vertices, this is a complete graph on 5 vertices. Now if you take any graph that contains K5, that also is going to be non-planar. You can prove that K5 is non-planar. That proof we will see. K33, that proof we are not seeing, but K33 also is non-planar. Any graph containing K5 or K33, that is also going to be non-planar. So if you take K6, the complete graph on 6 vertices, it will be containing K5. K5 will be a part of it, right? K4 will be a part of your any bigger complete graph. Any complete graph which contains more than vertices, it will contain K4 as a part. So K6 will contain K5, right? So it contains K4, K3, K2, everything, right? All these smaller vertices, the corresponding complete graph will be a part of it. So any graph need not be complete graph itself which contains K5, right? You have a six vertex graph like this, K5, and one vertex or energy is there like this. It is containing K5, then that part itself we cannot represent without edges are crossing. No such representation is existing. It's not planar, right? Which means any graph containing K5 as its part is not going to be planar, and any graph which contains K33 also is not going to be planar. Okay, you can see that any complete graph which contains less than 5 vertices, for example K4 itself, it is going to be planar, right? So this is your K4 standard representation using diagram. Now you can represent in an isomorphic form. In another representation I can give for the same graph, the cycle is there, and this edge also I am using inside itself the same edge. Now the other edge which was crossing your this diagram, this edge I am drawing through outside. So this particular representation is another representation of the same graph. It's an isomorphic representation, and this is a plane graph representation. None of the edges are crossing. So K4 contains a plane graph representation. It is planar graph. Okay, if you take K3, there is no edges crossing in the standard representation itself, so it's going to be planar. K2 also is planar, K1 is also planar, right? So K1, K2, K3, K4 are planar. That are the, in simple graph, that are the bigger graphs you can have for the corresponding vertices 1, 2, 3, 4, right? If you take the 5 vertex simple graph, which is the biggest graph you can have, it's K5, right? So K5 is not planar, and now any graph which contains K5 is not planar. K33 is not planar. Any graph which contains K33 is also not planar. Now proving K5, the complete graph on 5 vertices, is not planar. So we can discuss the idea in diagrams. That idea, if you are giving the proof, you have to give that idea as in words, right, with the diagram, supporting diagram. Okay, so consider the complete graph on 5 vertices. Label the vertices as v1, v2, v3, v4, v5. Okay, so first form the cycle joining these vertices. That is part of your complete graph. So those edges should be there in any representation you give, that those edges should be there, right? So we draw first that cycle. Now once you draw this cycle, the plane you draw it is splitted into 2 parts. One is inside of this pentagon cycle, and one region is outside it. Okay, now it is determining 2 regions, one is inside and one is outside. Now the edge from v1 to v3, every pair of vertices should be adjacent. So v1 to v3, so right now we have given v1, v2, v2, v3, v3, v4, v4, v5, v5, v1, these edges only, right? Every pair of vertices, these 5 vertices will be adjacent in your complete graph. So you have to include all such edges, but we are checking whether is it possible to include all these edges without a pair of edges are crossing each other in the corresponding diagram. So once we have drawn these 5 edges, we get a cycle, and the plane is represented into 2 parts, inside and outside. Now the edge from v1 to v3, either you can keep it outside or inside. So without loss of generality, if you are keeping it outside, a similar algorithm will continue, and we will show that it is not going to be planar. We are going to have edges crossing. So without loss of generality, let's take v1 to v3, we are drawing inside, right? v1 to v3, either it can be drawn outside or inside. Suppose we are drawing it inside, then the edges v1 to v5 and v1 to v4, we cannot now draw it inside, because if you draw it inside, it is going to cross your v1, v3. Therefore, once you draw v1, v3 inside, your v2, v5 and v2, v4 has to be drawn through outside region that you have determined, right? So this, in the next iteration or next stage, you have to draw your v2, v5 and v2, v4. It can only be drawn outside, right? Once you draw v1, v3 inside, v2, v5 and v2, v4 can only be drawn outside. So these steps are basically described in the proof here, so that you have to write it in words and give the supporting diagram also. Now what are the edges that are remaining? Okay, so for each vertex in a complete graph of n vertices, the degree has to be n minus 1, right? This is complete graph on 5 vertices. If 4 edges are there starting at a vertex, that all the edges for that vertex you have given. So for this vertex we have given 4 edges, so already, so it all, no more edges are going to connect with or going to have an end vertex with v2. Now for v1, 3 are there, so one more edge is there. For v3, 4 are already there, so no more edge. v4, 3, so one more edge. So v5, sorry, this is we have only reached here, right? So right now v2 has 4 edges, so all its edges are completed. v3 has 3, v4 has 3, v5 has 3, v3 has 3. So for these 4 vertices, one more edge is pending, right? So v1 to v3 already we have given edge, so v1 to v4 is there, and v3 to v5 is there. So suppose I am drawing v3 to v5, that you cannot draw through outside. If you draw any way, it is going to cross here this edge, so it cannot be drawn outside, so you have to draw it inside only. So you drawn it inside. Now one more edge is remaining. So now we are having, other than v1 and v4, all the vertices received 4 degrees. So now only one more edge will be there, which is going to make this graph as complete. So now that edge, v1 v4 edge, if you include, cannot keep it inside because it is going to cross this edge. Cannot keep it outside also. In any curve you draw, it is going to cross this particular edge. So there is, you cannot, this particular edge cannot be drawn inside or outside, okay, without crossing the edges, which means in any representation you give for the graph, we have shown now that the last edge cannot be drawn without crossing any of the edges, right? The last edge we choose in this iteration or this algorithm, it cannot be drawn anywhere without crossing the already given drawn edges. Without crossing them, you cannot draw the last edge. So that the graph K5, the complete graph on 5 vertices, it is not planar. There is no plane graph representation. It's not a planar graph. Okay. So now you can define operations in graphs like union of two graphs, intersection of two graphs, ring sum between two graphs, decomposition of graphs, fusion, deletion of a vertex, deletion of an edge in a graph. So this kind of operations you can define in graphs. Suppose you have two graphs G1 and G2. G1 has vertex at V1, it's at T1. G2 has vertex at V2, it's at T2. So for these two graphs, their union means a graph G3, which you will represent as G1 union G2. That graph G3 has the vertex set as vertex set of G1 union vertex set of G2, and edge set is edge set of G1 union edge set of G2. Okay. So union operation usually is done if there is one vertex common to both the graphs G1 and G2. Okay. So you consider this particular graph G1 where the vertices are V1, V3, V5, V4, V2 and these edges, and in G2 you have V2, V1, V2, V3, V6, V5 is there. Okay. So V4 is here, V6 it is not here, V6 is here, it's not here. So but you have common vertices V1, V2, V3, V5 are common in both G1 and G2. So what is the vertex set of G1? It is V1, V2, V3, V4, V5. For G2 it is V1, V2, V3, V5, V6. What are the edges in these graphs? That also you can, edge set also you can list out. Now what will be your G3, which is G1 union G2? It will contain the union of vertices of G1 and G2 as the vertex set. Okay. So it will be containing V1, V2, V3, V4, V5 and V6 as the vertex set. So all those vertices are what you are plotting first. Then you will start drawing the edges. Now if an edge is there present between a pair of vertices in G1 or G2, that will be there in G1 union G2. So between V1 and V2, we have the edge, B1 and V2 we have the edge A in G1, so that edge is there here. Now in G2 also the same edge is there, so there's only one edge between V1 and V2. Okay. Now V1 to V3, in G1 you have an edge B, and in G2 you have another edge G, so that you will be having two edges, parallel edges in the graph which is union, right? Both the edges will be present in the union, so you will be having parallel edges between V1 and V3. So in this fashion we are going to draw all the edges. So now V1 to V6, there is an edge in G2 which is edge, and V6 is not a vertex in G2, so all the edges present in at V6, that will be coming only from G2. So V6 to V5 we have an edge, V6 to, which is L, and V6 to V3 you have an edge. So these edges are exactly coming from G2. Now V4 is not present in G2, so all the edges you have at V4 in G1, that same edges you will have here as well, right? That are the only edges you have at V4. So D, which is to V2 from V4, F, which is to V5, that edges are there, right? So all these edges present in both the graphs we have given, present in either of the graphs you have given. Now V2 to V3 you have an edge here in G1, okay, and the same edge is there in G2 also, so you have only single edge, okay. So this way we will be forming the union of the graphs. Now what do you mean by intersection? The graph obtained by taking the intersection of the vertex sets and intersection of the edge set, that will be the intersection of two graphs. You are having G1 and G2, two graphs. The graph G3 found by taking its vertex set is the intersection of vertex sets of G1 and G2, and edge set is intersection of edge sets of G1 and G2. So you consider the graphs G1, G2, this ones. So what is the vertex set? V1, V2, V3, V4, V5 here, and V1, V2, V5, V7, V6 here. So what is the intersection? What are the common vertices? V1, V2 and V5 only. So these three vertices. V4 is there here, it is not here. V7 and V6 are here, but it's not there. So your intersection is V1, V2, V5. Now how about edges? Edges common will be between these vertices only, right? These are the only vertices in the intersection, means the edges that are common, if it is there, that will be between these vertices only. So if any other vertex is there, that edge cannot be there in the intersection, because the end vertices of that edges, it's not there in both the graphs, right? So you only need check for the edges which have these vertices as end vertices. So V1, V2 is such an edge. V1, V5 is not there here, so it won't be there. Now V2, V5 is there. So only these two edges you check whether it is in the intersection or not. V1, V2 it is here, and V1, V2 it is here as well, so that edge will be there. V2, V5 is there, which is E4. The label also you have to check. It is E4 here. V2, V5 is here as well, but it is E7. So V2, E4 is not common for both the graphs. E2, which is V1 to V2, that is common. Therefore only one edge is common, so it is E2. So that graph, which is the intersection graph, it will be what? Vertices V1, V2, V5 is common, edge E2 is only common. So this will be the corresponding intersection graph. G1 intersection G2 will denote it as. Now what do you mean by ring sum? Ring sum of two graphs. The notation is G1 circled sum G2, right? So it is a graph containing vertex set as union of vertices in G1 and G2, but the edge set contains the edges which are present in either one of the graphs, edges that are present in edges that are not common, right? Edges that are not common to both the graphs, that are the only edges present in your ring sum. So yeah, so basically in the intersection, not intersection also. So ring sum uses what? It uses all union of all the vertices from both the graphs, but the edges used are what? The edges that are not in the intersection, right? That are not common. That are the only edges that will be there in the ring sum. So G1 is this, G2 is this. What will be the ring sum? V1, V2, V3, V4, V5. So here there is V6, so all the 6 vertices will be there. So union of vertex sets, so you'll be having all the 6 vertices, and the edges which are not common for both. So you are having V1, V2, A. This A edge is there in both the graphs, so that won't be here in your ring sum. Okay. Now if you take any other edge, B it's not here, E it's not here, F is not there, D is not there in G2, C is not there in G2. So all the other edges in G1 will be present, and HK, and yes, C is there. C is there here. C is here as well. So this edge also won't be there. Okay. So only edges that you will not include is A and C. All and the other edges are either in G1 or in G2. Basically, you are taking G1 union G2 and removing the common edges that are present. So these two edges you have removed. G1 union G2. You obtain this one. So only those two edges you remove, you will be getting your ring sum. Okay. Now what do you mean by fusion? So by fusing two vertices, we mean the corresponding edge between those vertices now you are considering as a new vertex, a fused vertex, and every edge that are either incident to one of these fused vertex will be incident to the new vertex you are forming. So consider this graph. You have AB is an edge. So in the fused graph we are going to consider AB as a single vertex. Okay. So now give the incidence of the edges. Okay. So yeah, basically these two vertices you are identifying. Now any edge which are incident with A or B, it is incident with the new vertex you formed. So this edge is incident to A, which is from E. So E to A you have an edge. So E to the new vertex AB you formed, fused vertex AB you formed, that edge will be there. F is adjacent to B, therefore F will be adjacent to that fused vertex. D is adjacent to B, so it will be adjacent to AB. C is adjacent to B, so that will be adjacent to AB. Now C is adjacent to A also, therefore you will have basically parallel edges to AB from C. So C is adjacent to B and A, both the vertices which are fusing. C is adjacent to both of them, therefore you will be having parallel edges to the fused vertex. And A is adjacent to B, both the fused vertices are adjacent, therefore you will be having a loop at that fused vertex. This way you will be forming what is called the fusion of two vertices in a graph. Basically you are identifying those two vertices, and whichever edges are incident on either of them, that will be incident on the fused vertex. Okay, so that way we are forming the fusion. Now what do you mean by decomposition of a graph? So a graph G you are having, we will say it is decomposed into two subgraphs G1 and G2. If you get G1 union G2 is G, okay, and G1 intersection G2 is a null graph, the vertex set of G should be intersection of vertex set of G1 and G2. Basically all the vertices in G should be there in G1 as well as G2 when you consider the decomposition. So edge set should be union of both the edges in G1 and G2. So you consider this graph. Okay, so this is the graph G. Its decomposition you can consider this G1 and this G2. Both of them contain all the vertices of G, right? G1 contains all the vertices of G, G2 contains all the vertices of G. Now G1 contains these edges of G and G2 contains all the remaining edges, right? None of the edges are common as well, right? So this you can consider as a decomposition of G. So basically the decomposition should contain all the edges, all the vertices present in decomposition to two graphs of a given graph. It should contain all the vertices in the given graph. Both this decomposition subgraphs should contain all the vertices of the graph, and for the subgraphs it shouldn't repeat any, there shouldn't be any common edge between the decomposition subgraphs. But if you take the union of these two subgraphs, you should be getting the original graph G, right? All the edges of the graph should be either in one of the decomposition sets only, one of the decomposition subgraphs only. So any vertex you take in the graph is there in both the decomposition subgraphs, and any edge you take is exactly in one of the decomposition subgraphs. If such a way you can find two subgraphs, that subgraphs will be called a decomposition of your graph. Okay. Now what do you mean by deletion of a vertex operation? You have this graph, so once you remove or delete the vertex v2, we are also removing all the edges that are incident to v2. So the resulting graph will be, other than this vertex and all the edges that are incident at that vertex, all the remaining vertices and edges will be there. So v5 is there, but v5 to v2, that edge should be removed, therefore v5 becomes isolated. Now v6 to v7 will be there, but v6 to v2, v7 to v2, that edges are removed. v2 is also not there. Now v1 to v2, v4 to v2, that edges are also removed. v1, v3, v1. So that cycle part will be still there. So we are removing the vertex and all the edges that are incident on it to obtain the vertex deleted graph. Now what do you mean by deletion of an edge? If you delete an edge, you are not removing any of the vertices, you are only removing that adjacency, that edge only you are removing. So from this graph, suppose you are removing or deleting the edge e2, you are only deleting this edge, that edge only is deleted, no other changes happening in the graph. So that is the deletion of an edge in a graph.